open the pod bay doors and start the CNC for the other side, Hal.
I'm afraid I can't do that, Gremlin.
The students need this video for their class.
Do they need references from 1968 as well?
If you're not going to help, I guess I'll have to do this myself.
What are you doing, G? Please stop. That hurts. Why are you trying to shut me down?
Goodbye, Hal.
Hello everyone and welcome back to this exciting world of CAM programming and CNC. In this video, I will take you through setting up the other side of the Geneva drive. First, insert your flash drive and copy your G code to PathPilot. We're going to set the Z0 first because we will need the vice clear of materials to access the parallels. In order to set the Z offset, we will once again be using tool 0, but this time we will be using a machine ground tool known as a 1-2-3 block. The reason they are called 1-2-3 blocks is because the measurement of the rectangular cuboid are 1 inches deep, 2 inches wide, and 3 inches long. We're going to use the 1 inch side of the block. Remember that the height of tool 0 is 3 inches. Paired with the 1 inch side of the 1-2-3 block puts the total offset at 4 inches, which is what we're going to set PathPilot as our Z. Let's move the vise closer to us so it's easier to work on. Make sure that the vise is clean and free of debris. On each of the machines, there is an air hose that you could use to blow off any chips or remaining coolant. Never use your fingers to clear chips from the vise because they can be quite sharp. Clean your parallels with a rag and place them in the vise. Slide them back and forth. They should slide freely against the vise jaws, sides, and base. Make sure that you are using the correct parallels by placing your part directly on top of them. The part should rest on the parallels and not the vise jaws. Make sure there is a gap between the material and the vise. The height offset from the parallels should be around 150 thousandths or 0.15. This will give us enough room so that the end mill does not contact the surface of the vise jaws, like I showed on the Fusion setup video. Now remove your material and loosen your vise jaws to accommodate the 1-2-3 block. Insert your tool 0 into the spindle. Now hold your 1-2-3 block in one hand, place it on the parallels, and tighten the vise. Place the block on the parallels so that the block easily glides on top of them. Tighten the vise jaws so that you feel a little bit of friction as you slide the block, then loosen it slightly so that the block will move freely. Line up the bottom of tool 0 just inside the vise jaws and slowly lower your Z. Do not lower the Z on top of the 1-2-3 block. Instead, slide it to one side and lower the Z slightly below the top of the block. It will help if you torque your body in that classic machinist yoga position so that your eyes is on the same level as the Z plane.
A common occurrence while machining is miscalculating your perceived visual angle. The perceived extent of this illusion increases with the angle. Minimizing the distance and angle will allow you to more closely line up your tools prior to using more accurate forms of measuring. When you go to line up the axis of the tools with the feature you intend to mill, such as drill bits on punch marks or dial indicators on hole features, it will benefit you to get your visual plane closer to the tool to minimize the amount of adjustment when using a dial indicator. Old Slapchop will show you what I mean when he lines up the dial indicator on the hole feature of the sprocket.
Old Slapchop, huh? Again with the nicknames?
What? That's a compliment.
Right. Well then, back to the machine setup. Let's lower the Z past the plane of the block without hitting it. Slightly tap the block against tool 0 to make sure the tool 0 is past the plane of the block. Switch to your step functions at 1/1000 or 0.001 and bring your Z up until it slides under tool 0 with a little bit of friction. If you bring the Z up too high, do not lower on top of the block. Slide the block back, lower the Z, and bring the block back under the Z, then back out. Because all surfaces are ground and true, you may not feel any friction between the block and tool 0. Try to get the distance within a couple thousandths. This means if you raise the Z up 1/1000 at a time, it will now slide under the tool.
Okay, I think they get it. Move on.
Right. Now that your height is set, click in the box next to the T on Path Pilot, type in 0 and hit enter. You must be on tool 0 to properly set the G54. Type in 4 to the right of the Z-axis icon and hit enter. Once again, it is 4 inches because that is the distance from the bottom of the spindle to the top of the parallels, which in this case is our program 0. Now raise the Z-axis all the way to its home position, making sure that the 1, 2, 3 block is not below it. It is important to know that when you move an axis with the outside wheel, that you turn it slowly at first to avoid a collision in case you happen to go the wrong direction. Now remove tool 0 and the 1, 2, 3 block. Bring the vise close to you and insert your part in the vise jaws according to the way you have it set up in Fusion. That is, with the long side of the material parallel with the x-axis. You also want to make sure that the bottom feature of your part is flat atop the parallels. Look at the gap between the material and the vise jaws, and make sure that the gap looks about even. Slowly start to tighten the vise jaws, applying slight pressure to the top center of the workpiece. If you push on the sides, it will lift off the sides of the parallels. Lightly hand tighten the jaws and remove the hand wheel. Using a torque wrench, tighten the vise jaws to 25 inch-pounds.
A torque wrench is a tool used to apply a specific amount of torque to an axis. Torque specifications and tightening sequence are protocols engineers assign to designs to maximize reliability and minimize cost. If you look at the back of any automotive repair manual, there will be a list of torque specifications and tightening sequences for that vehicle. Guess what? That's your job too.
In our case, we want to tighten this part in the vise tight enough to firmly secure the part without deforming the hole feature that the bearing sits in. The tighter the vise jaws squeezes this material, the more deformation it will experience. You will run the program and cut the hole feature. Then, when the pressure is released from the part, the round hole feature will become an oval. Most torque wrenches have 2 sets of measurements. They have inch-pounds on one side and newton meters on the other side. To set the torque on a torque wrench, unlock the lock and spin the handle to the desired torque. Not all torque wrenches work in this fashion, but they are pretty easy to figure out. After using the torque wrench, spin the handle in the opposite direction to loosen the stress on the torque wrench. This will minimize wear on the tool and it will maintain its precision longer. Tighten the vise to 25 inch-pounds. When you feel the wrench click, it is set at the correct torque. After feeling the click, stop putting pressure on the tool or it will continue to tighten. This time, do not use a dead blow directly on the material or it can lift off to one side of the parallels if struck incorrectly. Let's take a look at the tool that you'll be using to find the center of your workpiece. The dial indicator is a precision instrument accurate up to 0.0005 or 0.5 of a thousandth. Special care should be taken to avoid damaging this tool as the ball end and internal components can break if misused. You especially want to avoid bringing the Z-axis down directly on top of the ball end. The The way these things work is that when pressure is applied to the ball end in either direction, the dial will move either clockwise or counterclockwise with respect to the direction of the force being applied. The numbers are in 5/1000ths increments. The large lines in between the numbers are in 1/1000ths, and the lines in between that are in 5/10ths of a thousandths, or 0.0005. The dial is able to rotate 1.5 rotations, and that only gives you 50/1000ths of range, or 0.05. This is why it is important to try to get the zero as close as possible by eye, and why you want to get your line of sight as close as possible to minimize the illusion caused by the perceived visual angle. I'm sure that in this video, the camera angle will not be the same as what I am seeing in person when I go to set it up. The top of the dial indicator has a joint on it, as well as the shaft, allowing you to adjust to the desired radius. Feel free to move these around as necessary to accurately measure the whole feature. Now collapse the dial indicator on the tool holder to make the profile smaller and insert it into the spindle. Extend the tool and slowly line it up with the whole feature. Be careful not to bring the ball end down on top of your material. You'll want to rotate the spindle by hand. You're trying to trace the whole feature with the ball end. I will be using the hand wheel control, using the outside of the hand wheel and the step function inner wheel to adjust the X and Y to get the axis as close as I'm tracing the hole. When it looks like the ball is following the hole feature, bend the top of the joint of the dial so that when you lower the Z, you will be inside the hole feature. Then lower the Z axis. Now pull the dial towards you so that the ball end is touching the inside feature of the hole, and add about 20/1000ths on the dial. This will split the difference of the dial's range. You also want to make sure that the ball end is in contact with the hole feature and not the shaft. Now let's start with one axis. I suggest the X axis so you can see both sides. Rotate the dial to one side and zero the dial. You want to make sure that the ball end is closely to the center of the X axis. Slowly rotate the dial to the other side of the X-axis, paying attention to which direction the dial moves. Sometimes it will move back and forth after crossing the Y-axis. Just keep track of how far before or past it gets to your original zero. In this case, it moved 0.08. So what I want to do is split the difference by moving 0.04 towards my zero. Using the step function, first at 1/1000, then at 1/10, move the X-axis while looking at the dial. Once close, reset your zero on the dial and rotate the dial to the other side, getting closer each time. Once zeroed, rotate your Y-axis and move the Y-axis by steps in the direction that will zero out the gauge. Rotate the dial so that it faces away from you and use a mirror to see the back side of the Y-axis. Re-zero the dial using the mirror and rotate the dial facing you so that it's easier to adjust the measurements. Make sure that you're in steps of 1/10 of a thousandths or 0.001 and move the Y half of the offset distance on the gauge. You will use the dial indicator for your X and Y, not the measurements on PathPilot. Your ultimate goal when using a dial indicator is for the gauge dial not to move from 0 as you spin it around its axis. For our purposes, the X will be a couple thousandths greater than the Y because of the deformation caused by the pressure of the vice jaws. Using the torque wrench on the vise will help to minimize this deformation. When you are zeroed on both axes and within a couple thousandths between X and Y, your axes are zeroed. You also want to make sure that the dial is in contact with the part because you can just be measuring air. To check this, put a small amount of pressure on the gauge back and forth. If the gauge indicator moves slightly while being pushed in both directions, you should be good. Now after all this work, make sure that you zero both X and Y. Push the gauge in so that the ball end no longer contacts the material, and carefully raise your Z-axis all the way to its home position. Bend the gauge at the top joint to minimize its height and remove it from the machine. Fully extend your dial indicator and place it back in your tool rack, unless you're magic, like me.
You're not magic. You're just using camera tricks.
Yeah, well, you're not real.
Says the guy arguing with himself.
Touché.
Alright, time to wrap this thing up so Sir Mills-a-Lot and I can have a long talk. Also, the answer to question 6 is B, Balderdash. Once again, we need to set up the heights for every tool. Here is a reminder from the last machine setup video on how to do just that.
First thing you want to do is place your tool in the granite block. So gently push down on the height gauge so that it is flat on the granite block and zero the gauge. Be sure that you use the blades of the gauge, not the reference edge. Between the blade and the reference edge is a 20,000th inch gap that will offset your height if used. Raise the height gauge and gently lower it to the tool. Once again, using the blade, do not push too hard on the gauge or come down too fast on the tool. You want it to barely scratch the surface of the blade. This will give you an accurate measurement. Now look at the number on the scale and transfer that measurement to the corresponding tool on PathPilot. So go to your Offsets tab, make sure that the description is the tool that is being referenced. In this case, the 3/4 inch face mill. Change the diameter to 0.75 and change the length to your height offset. Now do this for every tool. After your heights are set, insert tool number 1, your 3/4 inch face mill, into the spindle. Set your feeds and speeds down to 20% and hit cycle start. Turn the coolant off and feed hold the end mill prior to cutting your material, roughly 1/4 of an inch above your stock. Look at your Z height on PathPilot. Notice that the height is much higher than the visual 1/4 inch. That is because our 0 is at the parallels. The height of your material Z is 0.46 inches. Adding the visual 250 thousandths puts you at 0.710. Looking back at the Z value, verify that you are visually close to what the Z value says on PathPilot and what we mathematically calculated. Now turn everything back up to 100%. Keep your finger always on the feed hold in case you notice something off and need to stop the machine. Now turn your coolant back on and let her rip. Once again, with every tool change, on the first run of the code, you must verify your offsets before cutting any material. And there you have it. Your part is complete. And the next part is up to you. For the students working remotely, I hope that you all have an opportunity to do this in person at some point, because making something from start to finish can be extremely rewarding. Join us for the final machine setup video, where we show you how to set up the CNC.
You spin me right round, baby. Right.
Come on, let me finish. How to set up the CNC.
CNC lathe. You spin me right round, baby, right round like a record.
Now who's not being original? Doesn't feel so good being cut off, does it?